Goed, net so 'n paar konsepte. The first is reflection. You remember from grade 10, reflection, refleksie. In 'n lig kan reflekteer. Wat beteken as daar 'n glasblok is, hierdie is lig, daar is glas, of 'n spieël of water of wat ook al, dan kan lig kan gaan daai oppervlak tref teen 'n sekere hoek, aarde. Daai lyn werk glad nie. Hy gaan daai oppervlak tref teen 'n sekere hoek en hy gaan gereflekteer word, wat beteken hy gaan terug in sy oorspronklike medium in met 'n hoek van 'n refleksie wat gelyk is aan die hoek van daai invallende hoek. Okay? So reflection means that a light ray will bend back into its original medium when it strikes another medium. And that angle that it reflects with will be equal to that incoming angle there. Okay, but what you need to know here is that this thing is called a normal. It's just an imaginary line 90 degrees relative to the surface to just indicate, to give us a reference for those angles. Okay. The incoming angle and the reflected angle. Right, the second concept is the law of reflection. The law of reflection says that this reflected angle is equal to the incidence angle. Then the speed of light is 3 times 10 to the power of 8 meters in 1 second, and that is in a vacuum. And the denser the medium that it moves in, the slower it moves. Okay, so we talk about optical density. So if it has a high optical density, 'n hoë optiese digtheid, as hy 'n hoë optiese digtheid het, dan beteken dit 'n high optical density, then it means it slows down the light ray significantly. And if it has a lower optical density, then beteken dit dat hy die ligstraal minder laat verstadig. So hy laat hom nie soveel keer stadiger beweeg nie. Okay. So ons praat dan van wanneer 'n ligstraal deur 'n medium beweeg, as hy nie net gereflekteer word nie, as daai ligstraal nou daar by die normaal inkom, dan gaan hy in daai medium in en binne in daai medium buig die lig. So julle kan sien daarso is hy besig om daai kant toe te beweeg, wanneer hy in daai digter medium in beweeg, buig hy. So dit noem ons refraksie. That's refraction. Okay, so refraction is the bending of light as it goes into a medium with a higher optical density. And this is a medium with a lower optical density. Okay, and the law of refraction says that as a light ray moves into a higher optical density, that light ray will bend toward the normal. Okay, so you can see there that little light ray there is further away from that normal than that light ray there, right? Because this represents a medium with higher optical density, so the light ray bent toward the normal. Here, where there's lower optical density, the light ray is further away from the normal. Okay, the next concept is that as that light ray goes into that higher optical density medium, it bends because it's slower. But you just have to remember that the frequency stays the same. Okay? So if you remember from grade 10, the frequency determines the color eventually if it was visible light. Okay, that angle between the light ray coming in and the normal is called the angle of incidence, die invallende hoek. En daar is ook die invallende straal, that's the incidence light ray as well. And then that angle there between the refracted light ray and the normal is called the angle of refraction, die gerefrakteerde hoek. So as hulle vir jou vra om 'n ligdiagram te teken, dan is dit wat jy gaan doen. If they ask you to draw a light ray diagram, this is what you're going to do. Okay, next concept is Snell's law. So Snell's law concerns itself with light rays that move between two different optical densities, two mediums with different optical densities. So hierin het 'n ander optiese digtheid as hierin. En is die refraksie index. The refraction index. And the refraction index, N, is equal to the speed of light in a vacuum divided by the speed of light in that specific medium. So refractive index, no unit, is the speed of light in a vacuum, 3 times 10 to the power of 8, divided by the speed of light in a certain medium. So that's meters per second, this is meters per second, they cancel out to give us no unit. Okay. So the higher this refractive index is, the higher the refractive index is, the higher the optical density. So in other words, the slower the light will travel in it. Okay. So now Snell's law says this. It says that this medium has most now a certain refractive index. This medium has a refractive index. For our purposes, we're making this one the one with a higher refractive index, this one with a lower refractive index. So hier het 'n laer optiese digtheid, hoër optiese digtheid. Goed. Nou, as gevolg van die optiese digtheid is daai hoek van die tussen die lig en die normaal mos nou of groter of kleiner. So Snell se wet sê dat die optiese digtheid van 1 maal met sin van daai hoek van die invallende hoek is gelyk aan die optiese digtheid van die tweede medium maal met sin van daai hoek in die refraksiehoek. Okay, so this formula is the formula for Snell's law. Okay. So now they will ask you to do calculations with this. So they will tell you this medium, whatever this medium is, has an optical density of 1.3. This medium has an optical density of 1.4. This one has an incident angle of 40 degrees. What will be this refracted index? So if that's the question that they asked us, for example, then in this optical density, or refractive index, we will substitute the 1.3 there, we will substitute sine 40 there, we will substitute the 1.4, and then sine of that angle is our only unknown, and we'll solve for that angle by shift sign on our calculators to get that angle. Okay, so they'll always give you enough information so that you only have one unknown in this formula. Okay, also related to Snell's law is the critical angle. So a critical angle, what happens here is we have an incident light ray, and that incident light ray usually it would bend. If let's say this light ray is now coming from another medium that has a higher optical density, let's make it thicker. So it has a higher optical density than the second one. So this is higher optical density, lower optical density. Now, if it goes into a medium with a lower optical density, it will bend away from the normal according to the law of refraction. So what happens with a critical angle is now your refracted angle is equal to 90 degrees. So that light ray is going to run right here next to this surface between the two mediums. Instead of moving inside the medium somewhere there, it's going to run along the edge between the two mediums. So the critical angle is this one. The critical angle is the incidence angle. In other words, theta 1. That causes theta 2 to be 90 degrees. Okay? So a critical angle is not equal to 90 degrees because the critical angle causes 90 degrees there. So now they will give you a question, for example, where they ask, so what is the critical angle if we move from a medium with a refractive index of 1.5 to a medium with a refractive index of 1.3? And yes, that's the question. So what's the critical angle? Then you're going to substitute in N1 sine theta 1 is equal to N2 sine theta 2. Now you're going to substitute that N1 is 1.5. You are looking for the critical angle. So this is your unknown. This second refractive index is 1.3 and the refracted angle is 90. Per definition, that's what a critical angle is. A critical angle is the angle of incidence that causes the angle of refraction to be 90 degrees. So that's what your formula is going to look like, and then you're just going to solve for that unknown angle. Okay, next concept is total internal reflection, totale interne weerkaatsing. Dit gebeur wanneer die lig beweeg vanaf 'n hoër optiese digtheid na 'n laer optiese digtheid. So julle onthou nou wat gaan gebeur as hy van 'n hoë na 'n laer optiese digtheid beweeg, gaan hy mos nou wegbeweeg van die normaal. So daai hoek gaan groter word. Nou het ons nou net gesê met 'n kritieke hoek gaan daai gebuigde hoek, daai gerefrakteerde hoek gaan 90 grade wees, so hy gaan so gelyk met die oppervlak tussen die twee mediums wees. Maar wanneer ons totale interne weerkaatsing het, dan is daai invallende straal, hierdie ene wat hier inkom, the incidence angle is greater even than the critical angle. So hy is groter as die kritieke hoek, so nou wat gaan gebeur is daai gerefrakteerde hoek gaan nie 90 grade vorm nie, maar hy gaan 'n hoek vorm wat groter is as 90 grade. So daai gerefrakteerde hoek refrakteer heeltemal terug in die oorspronklike medium in. Want die gerefrakteerde hoek is nou groter as 90 grade. So, hy buig terug in die eerste medium in. Dis totale interne weerkaatsing. En hierso gaan daai twee hoeke nou nie ewig groot wees nie, want dit is dis eintlik refraksie wat hier gebeur. Dit is nie gewone refleksie nie. Okay. So dan is daar nou 'n paar toepassings van hierdie totale interne weerkaatsing. En een van die hooftoepassings is met optiese vesels. Optiese vesel, optical fiber. So in julle handboeke is daar 'n duidelike uiteensetting van al hierdie toepassings daarvan. So jy moet dit